This is just a video on an introduction to loci, and here we have a mechanism which is going to plot a point or points which is of C through all these points, where B is a fixed point and so is A. C1 rotates around the circle, where A to C1 is the radius, C2 is the locus that we're going to plot. These distances never change, so the distance from B to D doesn't change, C2 to D doesn't change, and neither does D to C1 or A to C doesn't change. So if we go ahead and turn the animation on, you can see as C1 moves around the circle, it also causes D to move, which causes C to move around in a motion like this, and it plots all these points. As you can see, B and A are fixed, so they don't move a lot. It's only C1, D, C2 that move, and C2 plots all the points of the locus. As it rotates from this half to this half, it draws a flat line, and from this half to this half, it draws a curve, like so. I'm just going to talk about how this ellipse here can be a locus. So the point H here is the locus point, and this point H will create a path all around here, and it will trace out an ellipse. So the line segment AB represents the major axis, and that is equal to 12. The line ED represents the minor axis, and points G and F are the focal points, and they are found by getting half the major axis from, say, C to B or C to A, and swinging it from D or E, and hitting the major axis to find both points F and G, which are the focal points. Since H is always a point on the ellipse, if you join F to H and G to H, the distance from F to H and G to H, if you add them together, it will always be equal to the distance of the major axis. So, like shown here, F to H is 1.29 and G to H is 10.71. When you add them together, it's 12. I'm just going to show you how, no matter where the point H is on the ellipse, if it's joined to FH and to GH, if you add FH and GH together at any time, it will sum up to 12. So I'll just play it. So as you can see, no matter where it is on the ellipse, as H moves around, the product of FH and GH will always be equal to 12 all the time. So as F to H decreases, G to H increases, and so on. And let's pause it there. So this shows how the points F to H and G to H are, if you add them together, they will always sum to the length of the major axis, and H is the locus and plots the path all around the ellipse. How's it going? William Hurley here, just explaining how to draw an ellipse using concentric circles. As you can see, I have my major axis B to C and my minor axis D to E, and I've drawn in my minor auxiliary circle and my major auxiliary circle. The point H here is a point on the ellipse, and it's a locus point that plots the path of the ellipse all around. So as H moves around, it plots the ellipse all the way around using this concentric circles method. So in manual drafting, we would usually use 60, 30 and degree set square to draw lines out here at 30 degrees and 60 degrees in each quarter. But in this case, I've just drawn any line at any angle, and I've drawn it from the center out through the minor auxiliary circle to the major auxiliary circle. And using this method, as this line intersects the minor auxiliary circle, you draw a line parallel to the major axis out, and as this line intersects the major auxiliary circle, you draw a line parallel to the minor axis, and where these two lines meet is a point on the ellipse. So, and as the point H moves around, the point F here will also move, and the point G. The point F move around the major auxiliary circle, and the point G will move around the minor auxiliary circle. And the distance from G to H and F to H, the product of those two will never ever change. So as G increases, F will decrease, and so on. So I'll just play the animation. So as you can see, H plots the points of the ellipse all the way around. And always, the distance from G to H plus the distance from F to H will always be the same as it moves around. How's it going? William Hurley here, just explaining an ellipse using the Trammel method. So here we have on GeoGebra a circle, and we have the major axis, which is L, or L to J, in here, and we have the minor axis, which is here. Now, using the Trammel method, to plot the F plots the point of the ellipse all the way around. So it plots the whole path of the ellipse as it goes around and around. And let's play the animation here. As you can see, the distance from C to F is the length is half the major axis. So that distance never ever changes. It is always equal to half the major axis. And as it moves around, it's plotting the point of the ellipse. So the Trammel method goes by where this point C here will always be on the minor axis, always, and never ever leaves. And the same point with D. D will always be on the major axis, it never ever comes off it. So as C moves up and down the minor axis, D then moves around up and down the major axis, and as they move, they carry F along in a motion like this, and it creates an ellipse, and this is known as the Trammel method. When you turn animation on for the point B here, it drags these points all the way around. The line R and Q here, the sum of these distances never ever changes. As they move around, they will always be equal to a certain distance. So Q to B plus R to B is the same, always the same, as it moves around, creating this ellipse.